start. Okay, so let's continue. So, like a quick summary, so we started with policy gradient theorem, which kind of proved that we can develop efficient policy gradient methods, right? Like, and we looked at two different algorithms, like so reinforce and reinforce with baseline, right? Now, if you think about reinforce with baseline, right? Like, so maybe let me rewrite reinforce with baseline, like as a recap. So it was theta t plus 1 is equal to theta t plus alpha times, right, gt minus v of stw gradient with respect to ln pi of at given st, right? So this was reinforced with baseline. So now you can see that we are already using both the policy function approximation and also the value function approximation, right? Now, if you remember, like the beginning of the lecture, I told you that like there are ways to combine policy methods and value-based methods, like so which is the idea of actor-critic method, right? Like so, however, we will not call this reinforce with baseline. We will not call this as actor-critic method yet, okay? Then what is an actor-critic method? So that's what we are going to discuss now. Now, if you think about this particular policy gradient method, which is reinforced with baseline, right? So now you do have the value function estimated, right? However, there is no bootstrapping happening here in the sense the value function that you have estimated is just for the first state, like in the transition, right? So in vanilla policy gradient methods, even if you estimate value function, it is going to be only for the first state in the transition, okay? The GT is still computed based on the sample return, which means this particular algorithm still needs to wait for the entire episode to over, right? So now it might be possible in some like small episodic tasks, but this is definitely not possible in continuing tasks or like really long episode tasks where you have to act and learn faster, right? So this is where actor-critic methods come into play. So actor-critic methods are going to use value functions for more than a baseline, okay? Now, given that you're already learning a value function, right? So like, why not approximate this GT with one step return or even n step return for that matter, right? So if I approximate GT with one step return, okay, so then I'm actually using the value function, like even to decide things on the moment, right? Like so, or in other words, I'm using the value function for every state in the transition, like because I'm approximating everything else with the value function. So it's going to be something like TD learning, right? Like so, like you don't need to wait for the episode to end. You can immediately learn by just taking one action, right? So that is what actor-critic methods are. So let me write the algorithm. It is really simple. So theta t plus 1, okay, is equal to theta t plus alpha times, okay. So instead of gt, I'm going to call this as gt to t plus 1, my one step return, okay, minus v of st given w, okay. I think there was a thing here, and then gradient with respect to ln pi of at given st. Is that clear? So now I can actually expand this one step return. So this is theta t plus alpha times rt plus 1 plus gamma times V of st plus 1 given W. Okay. Oh, sorry. Minus V of st given W, right? The whole thing multiplied by gradient of, I'll just put gradient ln pi to avoid rewriting it again and again. Okay, so but you know what it is. Is that clear? Now we know what this is. This is just the TD error, right? So now the actor-critic method is going to be theta t plus alpha times the TD error gradient with respect to ln pi of at given st theta t. Is that clear? So now how do I learn the value function now? So if you're using Monte Carlo for learning value function, then there is no use in switching to this notation, right? Like, so the whole point was to avoid waiting for the episode to end. So, so now, just like how we switched from Monte Carlo to TD-like approach for the policy, we will also switch for the actor, like for the critic. So the critic is my value function. So we will learn the value function using, let's say, semi-gradient TD. Is that clear? So here is a simple actor-critic algorithm. Okay, so here you have a one-step actor-critic. You can extend this for n-step actor-critic if you want, right? So you have a different, like as usual, the differentiable policy, differentiable function approximation for state value, right? Two separate learning rates, right? Now you start. You're going.
Sorry, could I? Piss them off.
I think I forgot to turn off the unmute button for people in Zoom. Okay, so now you're going through these episodes. Okay, so you take an action, you observe S dash on R. In vanilla policy gradient, you will complete the episode before making the update. Now you don't need to complete this anymore. You can easily compute the TD error, right? And you can do semi-gradient TD for updating your W, and you can do the actor-critic update for updating your policy. That's it. Is it clear? Yeah?
So we started with policy gradient and other stuff because we thought that the value function approximations were not working out for us. And we are doing now value function, we are learning value functions and doing more stuff. So like, isn't your—
Yes, so the difference is the learning, the value function that you're learning, right? It is only aiding the policy. So your goal here is not to learn the value function. So you're not learning the value function and then constructing a policy by doing the usual max thing that we did with the value based.
So the advantage is that we are now learning a stochastic policy and not the deterministic thing.
Yes. Is that clear? Any questions about actor-critic? Well, unfortunately, the book does not have any examples for comparing policy gradient and actor-critic. However, you are going to do that in your assignment. So your assignment 3 is basically implementing reinforce and actor-critic for a very simple environment and study how they perform relatively. Okay. Okay. Any questions so far? So far we have covered policy gradient for episodic problems. Well, of course, actor-critic can be used even for continuing problems. Okay. So however, we also discussed a third class of problems, I think last week or last week, like so continuing problems without discounting, right? So now the question is like, so would policy gradient theorem work even if I'm using even if I'm in the continuing problem setting? Sorry, setting with no discounting. Okay. Now, the good news is policy gradient theorem still holds, like when you use continuing with when you're in the average reward setting. Okay, so when you're in average reward setting, policy gradient theorem still holds, which means you can just extend things like how, okay, we are not going to do that extension now. Okay, so like you can extend these algorithms to the continuing case by yourself. Like, so like you can just do the algorithmic extension, the theory follows. Okay, so however, we'll just quickly see how the theory follows. Okay, so like we will not prove it completely, but like we will give you a sketch of like how policy gradient theorem still holds. Like the proof is really simple for continuing case and average reward setting. Okay. Now remember that in the case of average reward setting, our performance metric is not the value function of the state. Like our performance metric is R pi, right? So we care about maximizing R pi, the average reward that you get from the whole episode, right? So my J of theta is going to be R pi. So a quick recap of what is R pi. So it is limit h tending to infinity, right? 1 over h, summation over t is equal to 1 to capital, 1 to small h, expected RT given S0, and you take actions from 0 to t minus 1 following pi. It is literally the average of all the returns that you have, like all the returns from the episode, right? So now this can be written as limit t tending to infinity, expected value of RT given S0, A0 to t minus 1, right? And we also had the expanded equation for this, which is summation over all possible yes, mu of yes, summation over A, pi of A given yes, sorry, A given yes, summation over S dash R, P of S dash R given S comma A, the whole expectation multiplied with the reward R, right? So where mu is our steady state distribution, right? So mu of S is given by limit t tending to infinity, the probability of being in that state, given we followed the policy. Like as time goes to infinity, what is the probability of visiting the state? Like by the time the probabilities have converged, that is the steady state distribution, right? Like so now the other way of mentioning steady state distribution is summation over S, mu of S, summation over A, pi of A given S theta, P of S dash given S comma A is actually mu of S dash. Like you take a step, you go to the same distribution again. Okay, so that is a steady state distribution. I'm reminding you here this because we are going to use this. Okay, is it clear? Now, another reminder. So in the case of average reward setting, the return GT is given by RT plus 1 minus R of pi, right? There is no gamma here. So then plus RT plus 2 minus R of pi plus RT plus 3 minus R of pi and so on. So if you remember, we called this as a differential return, right? Like similarly, we have differential value function and like state value function, differential state action value function and so on. And also differential version of the Bellman equation, right? Is that clear? Okay, so now let us actually prove that the proportion that we saw in the policy gradient theorem, right? Like so, it is indeed true for continuing case. Okay, now remember that there is a small change here. The J of theta that we care about is R pi. It's not V pi of S. Okay. However, let us start with V pi of S. So what would be the gradient of V pi of S? So we're going to do the same steps again, but this time much shorter. So the gradient of summation over A, pi of A given yes, Q pi of S comma A. Right? Now you do the UV, like I'm going to skip a step here. So I'll bring the summation out and then I'll do the UV rule here. So it's derivative of pi of a given s, q pi of s comma a, plus pi of a given s, del q pi of s comma a. Just the product rule, right? So now I can expand this. So this is where the average reward comes into picture. So summation over a, the gradient of a given s, q pi of s comma a, plus pi of a given s multiplied by the gradient with respect to summation over s dash r, okay, p of s dash r given s comma a, okay. Instead of r plus v pi, we are going to have r minus r theta plus v pi of s dash. Is that clear? My average reward is actually a function of the policy. Okay. Now, summation over a, the gradient of pi of a given s, q pi of s comma a, plus pi of a given s, okay. Now, let's look at what is inside, right? So now you can see that the r thing would obviously disappear when you're computing the gradient because the gradient is 0. Now, the r theta is not a function of s dash, right? So I can just bring it outside. So this becomes minus gradient with respect to r theta plus summation over s dash p of s dash given s comma a gradient with respect to v pi of s dash. Again, I have skipped a couple of steps here because, like, you will have summation over s dash comma r. Then there's no r, so you remove the r, right? So I just skipped the trivial steps here. Okay, now this is fine. Okay, so now I'm going to do a little bit of rearranging here. Okay, so I will directly write it, but it is easy. So now this left-hand side, you had gradient with respect to v pi of s, right? But what we really care about is v gradient with respect to r theta, right? So I'm going to bring this thing to the left-hand side. So gradient with respect to r theta is equal to summation over a, gradient with respect to pi of a given s, q pi of s comma a, right? Plus pi of a given s, okay, summation over s dash, p of s dash given s comma a, gradient with respect to v pi of s dash, okay, so the whole thing minus gradient with respect to v pi of s. Is that clear? So, well, maybe there are a few steps that are missed here. The step is when you bring that summation over all possible action pi of a given s times this is not a function of a, so that summation becomes 1. So that is why I freely moved this to the left-hand side instead of worrying about the summation. Is that clear? Okay. Now you can see that the left-hand side, there is no state involved, right? Of course, this is average reward setting. We don't care about this value of one state. So there is no state involved in the left-hand side at all, right? So similarly, there is no state in the right-hand side, like in the outer loop. So what I can do without loss of generality is I just add summation over all possible states mu pi of s. Okay. Now that is okay because summation over s mu pi of s, like for all the mu's, is 1, right? So I will take this equation, copy, come on, I'll take this equation, okay, and just add, okay, I know this is getting ugly, just add summation over s mu of s. Now this is okay because this summation is actually 1, okay. Now, however, the advantage is now we have the policy gradient formation. So now you can see that this is actually equivalent to summation over s mu of s summation over A, the gradient of pi of A given S, Q pi of S, comma A, which is what we want, right? So this is what the policy gradient theorem gave us for the episodic case. Plus, you have the second term, which is summation over S, mu of S, summation over A, pi of A given S, summation over S dash, pi of S dash given S comma A, the gradient with respect to V pi of S dash, minus summation over S, mu pi of S, gradient with respect to V pi of S. Is that right? Okay. Now, I can do a little bit of restructuring here, okay? So summation over S, mu of S, summation over A, well, I wish I can copy paste this. Okay, Q pi of S comma A, so this is the same thing, okay? Plus, the second thing, right, like I can move summations around. So this becomes summation over S dash, summation over S, mu of S, summation over A, pi of A given S, P of S dash given S comma A, gradient V pi of S dash, minus summation over S, mu of S, gradient V pi of S. Now, what is this particular thing? It is mu of S dash, right? So this essentially becomes summation over S, mu of S, summation over A, well, the whole first term, okay, plus summation over S dash, mu of S dash, the gradient, right? Minus summation over S, mu of S. Okay, now these are two summations that are canceling each other, right? So here we have our final value. So the gradient with respect to J of theta is actually equal to summation over S, mu of S, summation over A, the gradient of pi of A given S. Is that clear? So in fact, the policy gradient theorem works for continuing case, so you can extend all the continuing algorithms and you have guarantees. Is that clear? Okay, so far we discussed mostly, like if you have observed closely, just on policy gradient algorithms, right? So we discussed reinforce, we discussed reinforce with baseline, reinforce with Actor-Critic. Now you can do all these things for continuing case as well. But this is all on policy gradient algorithm. So now, how do we do off policy methods? So before that, can someone explain me, like what could be the potential benefit of developing an off policy gradient algorithm?
You learn one policy and then you learn almost every other policy. Like, the values and
okay, so what was the use for off policy methods in value-based methods? Like, so why were we learning off policy methods? There were a couple of benefits there.
Higher explanation. So you can have a deterministic policy.
You can have like you can learn about a deterministic policy, like while having a behavior policy which is stochastic. Okay, then I think the second advantage is probably what you mentioned, right? Like so, like you can actually use all the data from the previous policies, right? Like for example, if you think about DQN, like where you had this idea of replay buffer, right? So the replay buffer had all the transitions from old versions of the policies, right? Like so, in that sense, it is not even the data from the current behavior policy. It's the data from the old behavior policy. So when you have such data and you can make use of the data, then you can become extremely sample efficient, right? So that is another reason like why you should prefer off-policy methods. And in the case of policy gradient algorithms, it is actually the second reason which is more meaningful here, because you're like anyway your policy is anyway stochastic, okay? Oh, by the way, so we talk about stochastic policy gradients throughout this lecture and probably for this course, but there are also deterministic policy gradients, okay? So probably it's a bit more advanced. Like if you are more interested, like you can of course read about deterministic policy gradients. Like we have similar policy gradient theorem when your policy is deterministic. Well, first of all, if your policy is deterministic, how do you learn? Like it looks absurd, right? Like so that's why it's a bit more complicated. So we will not talk about deterministic policy gradients in this course, but we will just stick stochastic policy gradients. Okay, so so in that sense, like the main advantage of off policy gradient is sample efficiency. Okay, now in the case of off policy gradient, right? So if you remember, like all the off policy methods, we have a separate behavior policy, and we have to do course correction, like by using what? Importance sampling, right? Like you do some importance sampling. Now, J theta for my off policy method is going to be summation over all possible yes, okay? Instead of mu pi of yes, it's going to be mu b of yes. Okay, pi is my target policy, right? B, if you remember, is the behavior policy, right? Now your distribution is based on the behavior policy, not based on the target policy, right? So it's going to be mu b of yes, summation over a, q pi of, q pi of s given s, okay. I'm really translating notations here, s comma a. Okay, so pi of a given s theta. Is that clear? Well, it would be more intuitive if you put probability first and then q, but they're both same. Okay, now this is basically expectation where the states are sampled from mu b of s. Okay, it's a different expectation. In the original on policy case, like it was expectation with respect to the mu pi. Okay, so you have summation over a. Okay, I'll just make it more easier. So pi of a given as theta, q pi of s comma a. Is that clear? So where this mu b of s is basically the stationary distribution of the behavior policy. Okay. So however, we know that we care about the target policy, right? Like we want gradients with respect to expectation from target policy. So how would we do that? Like we just add importance sampling. Okay. Now, every time you make changes, right? Like you just need to make sure that the policy gradient theorem holds. Okay, otherwise you are in trouble. So like all these algorithms are developed with policy gradient theorem as the base. Okay, so proving policy gradient for off policy methods is a bit more complicated. Okay, so like if you are interested about the proof, I will refer you to, I'm not sure if I have the reference right now. Yeah, I do have it. So if you are interested in the proof of off policy gradient theorem, like I would refer you to, I'll give all these references in today's reading, okay? But I'm going to give a lot of references. You don't need to read all the references. Okay, so this is for people who are interested in exploring more. So this is Degris, White, and Sutton, 2012. Okay, so however, like we will see a very small hand wavy argument why this could be the case. Okay, so now the gradient with respect to j of theta is given by gradient with respect to expectation or for state coming from mu b, okay, summation over a, okay, pi of A given S theta, Q pi of S, comma A. Is that right? Now I can do the product rule. So this becomes X gradient, sorry. I will do all the steps together, okay? So I'm going to bring the gradient inside. I'll do the product rule. So this becomes expectation. The expectation is still with respect to mu B, okay? Of summation over all possible actions. Q pi of S comma A, gradient of pi of A given S theta, plus pi of A given S theta, Q pi of S comma A, gradient of Q pi of S comma A. Is that clear? Now, this particular thing, right? So this is what difficult to compute, right? So that is why we spent all our time improving policy gradient. But for the off policy case, we are going to ignore this. And we're going to approximate the thing, okay? We're going to approximate the thing with E of S given mu P, summation over A, Q pi of S comma A, the gradient with respect to pi of A given S comma. Okay? So why this approximation is true, like is good approximation, like so that argument is complicated, like it's there in the paper. But for now, let us just assume that we can afford to make this approximation. Okay. So once you make this approximation, then things are trivial. So like you are still having expectation with respect to yes coming from mu B behavior. Okay. Summation over A. Okay. Now, if you remember, like in regular on policy case, we had pi of A given S, Q pi of S comma A, the gradient with respect to pi of A given S divided by pi of A given S. But I removed thetas here, right? This is what we did. Now we also need to do correction for the behavior policy. So I'm also going to multiply and divide by B of A given S. Is that clear? So now this becomes expectation with respect to my behavior policy B, okay, pi of A given S multiplied by B of A given S, okay, Q pi of S comma A, gradient with respect to ln pi of A given S. Okay, I'm really being loose here with thetas. So, but by now you should be robust to where is theta, where is not theta. Now, this looks very similar to the on policy situation, except for the fact that I have added this importance weight. Is that clear? So now if you want to develop off policy algorithms for policy gradient, you can do that by yourself. Okay. Now, finally, I want to talk about like, so far we looked at linear function approximations, right? Like, so now you can extend these things to usual like neural network versions, like which is deep reinforcement learning, right? Like, so now we will just see one example for this algorithm, like one example policy gradient algorithm, which is very trivial now. So, which is the idea of A3C, okay? So A3C stands for asynchronous advantage Actor-Critic. Okay, so this is by Mila et al. 2016. This is approximately the same group who also did DQN, okay, which is the deep version of the Q learning, right? So this is a deep version of Actor-Critic, okay? Now the idea here is really simple. Like you're going to have a neural network, okay, which is your policy. Like you give the state, okay. Now this neural network is going to produce two outputs. The first output is pi of A given S for all actions, okay, which is my policy network, Now we also need value function approximation, right? Like we need state action value function approximation specifically. No, we just need state value function. Yeah, we just need state value function, which is good. So there is only one entry here, like which is v pi of s. Okay. So now the advantage here is like I'm using same function approximator, but just in the top I have two different types, right? Well, of course you can design two separate neural networks, like one for pi of a given s, and one for, let's just call this neural network 1, neural network 2 for v pi of s. Okay. So sometimes this helps because whenever there is a lot of clash between these two things, like so, it is going to be difficult to learn both with same function approximators. Sometimes it helps to just learn two things separately. Okay. Now you are going to update your v pi of s by using the usual TD error, and you're going to update this with your actor-critic update equation. Okay. Now they call this algorithm as advantage actor-critic. Like because another way to look at the error that you have in Actor-Critic, right? Like so, if you remember, you are multiplying your del on pi with gt t plus 1, right? Minus value of the state given w, right? So theta t plus 1 is equal to theta t plus alpha times this thing, right? Now, so this is basically the expected value of q of s comma a, right? And this is actually the expected value of v pi of s, right? Now, this difference between these two things, right? Like so, in a particular state, there is a value for the state, okay? Now, each action in that state is going to have different values, the state action values, right? Now, this difference is the advantage of taking this particular action in this state. If it is a good action, then the advantage is going to be positive. If it is a bad action, the advantage is, there is no advantage, right? Like so, so this is just a different terminology. So we are going to call this as the advantage term, okay? So like another way to write this whole thing is as theta t plus 1 is equal to theta t plus alpha times the advantage multiplied by del on pi. Okay, so that is why they call actor-critic as advantage. And well, there has to be some tricks to make this work, right? Like in the case of DQN, can someone tell me what were the tricks used in DQN?
Use copy of.
We were using target network to copy and make things less non-stationary, and we were using replay buffer to break the correlation, right? So similarly, there is also an important trick that is used in making this actor-critic, neural network actor-critic work, which is the asynchronous part. Okay, so the asynchronous part just means that you actually have a distributed training setup. Okay, where you have one global network parameter. Okay, however, you can use many computational nodes. Okay, like agent 1, agent 2, agent 3. This is agent, okay, not action. Agent 1, agent 2, agent 3, right? So, for example, you can use 100 different agents acting in parallel, okay? They all compute the updates for both the value function approximator and policy approximator, and you send all this thing to the server, okay? Now, this server is going to asynchronously get this update and pass this to the actors once in a while, okay? There's a lot of staleness involved here, like because like they don't have up-to-date parameters all the time. But the advantage here is like you can learn significantly faster because you are running many actors in parallel. Okay. Now there is also A2C, which is the synchronous version of Actor-Critic. Well, so the idea of A2C is like exactly like A3C, except for the fact that you're going to synchronize the gradients. You don't do this asynchronously. Okay, so A2C would look something like this. So you have, Okay, I'll just do this. So you have a coordinator, okay, which takes all the gradients, integrate, make the update, make sure everyone has the right thing, and then continue. Okay, so depending on like how you're going to train your algorithms, you'll use A2C or A3C. For example, if you have a lot of CPU cores, then you can go for A3C because you can run all these actors in parallel, right? Like, however, if you're running A3C in GPU, it's really inefficient because you cannot have 100 GPUs just doing one action, right? Like, so on the other hand, like methods like A2C can be efficiently implemented in GPU. So you have CPU for computing the grades. Like you have CPU for making actions, then you compute all the gradients and update with just one GPU big operation. Is that clear? Okay, so finally, like I want to quickly talk about one of the biggest advantages of using policy gradient method, which is basically now it is almost trivial to handle continuous actions. Okay, so why do I say that? Because I have a policy which is parameterized, right? Now, instead of outputting a discrete distribution, I can just output a continuous distribution. Like for example, often we will parameterize continuous actions using a Gaussian distribution. Okay, now a quick recap of how Gaussians will look like, right? So here are some sample Gaussians. Okay, so the normal distribution or Gaussian distribution has the following PDF. So P of x is given by 1 over sigma square root of 2 pi x of minus x minus mu whole square divided by 2 sigma square. Right? Now, we want to use this for coming up with a continuous action, right? Now, what are the parameters of this Gaussian distribution? So mu and sigma, right? So these are the only two parameters of this Gaussian distribution. So I can now have a function approximator for mu, a function approximator for sigma, and I can construct the PDF. I can maximize the probability, right? So it is very easy. So now we're going to have pi of a give s theta, okay, to be 1 over sigma of s theta. Given a state, I'm going to estimate the sigma by using some parameter theta, okay, square root of 2 pi x of minus the action minus mu of s comma theta, the whole square, divided by 2 sigma of s comma theta, the whole square. Is that clear? Now my theta is going to have theta mu and theta sigma. Like for example, if we are using linear function approximator, then this becomes mu of s comma theta is equal to theta mu transpose x mu of s, and sigma of s comma theta is theta, sorry, the variance has to be positive, right? Yeah, so the standard deviation, we're looking at standard deviation here. The standard deviation must be positive. So we're going to approximate that by using exp of theta sigma transpose x sigma of s. Is that clear? Now, one can use two separate function approximators for mu and sigma, or like as we saw in A3C case, like you can have a neural network, for example, which takes the state and gives you an estimate for mu of s and sigma of s. And then you construct the probability, like probability from which you can sample, right? Like you sample from this learned Gaussian that is going to give you the action. Is that clear? Any questions? Okay, so I know we have to finish, but give me a minute to quickly summarize what you have seen so far. So we looked at policy gradient methods, right? Now, specifically, like we looked at reinforce, which is the very basic Monte Carlo policy gradient, right? We improved it by using reinforce with baseline. Then we also looked at Actor-Critic, right? And we discussed about how to do all these things with off policy. Oh, we also discussed how to do this with continuing settings or average reward setting. And we also discussed how to do these things with continuous action space, right? So that summarizes the second class of reinforcement learning algorithms, okay? Now, this is going to be your assignment 3. Now, moving forward, like so next week, we are going to see yet another class of reinforcement learning algorithms, but this time we're going to move from model-free methods to the idea of model-based methods. Like so far, we thought that we don't have access to the model, so we should just learn the value estimates without the model, right? Like so. Now, what if I can also learn the model of the word, okay, an approximation for the model of the word? So how can I use this idea in both policy gradient or value-based methods, right? Like that is what we will focus on the next week. And next to next week, like we're going to see some advanced, starting from next to next week, we're going to see advanced topics. Like, so the first would be the idea of eligibility traces to improve value-based methods, okay? And that week is going to be a guest lecture by a research scientist from Microsoft Research. So Ham Wan Sain, like, so who is the lead for the reinforcement learning team at Microsoft Research Montreal. Okay, so like I invited him because some of the algorithms that we are going to discuss in eligibility traces, like he is the inventor of those algorithms. So he's going to explain the intuitions behind the algorithms that he developed. So it should be very interesting. So that is the week after next week. So, okay, so we will stop here and I'll take some questions if you have any. We can officially end the class, like, but this is my office hours, so.